Thank you.
Hey, Sal,
Anyway, yes,
about
sir.
about the super force, or
Yes,
I always called that the Planck force.
yes, it is
And
the Planck force.
it is.
Yes,
And all these Planck scale objects, Planck length, Planck time, Planck
yes,
force, Planck
yes,
charge, even like the fine structure constant, I look
right,
at it's E squared over the Planck charge squared.
right.
It's same, it's all in there. Um, I just see these as a baseline based on our own man-made constants that we created to equate to the units we defined. And it's like, to me, it's like you have a deep bucket with a flat bottom base, and up here on the top, the wind's making the top ripple, and that's what we have to work with. And down
Right.
here at the bottom of the deep bucket, you got a baseline that you can't change.
Yep.
Agreed. Good observation. Now
So
let
none
me
of
say what
that,
I have
but
to
none
say.
of that really has any, let me finish. None of
Okay.
that really has any effect on anything we can do other than reference it as a common baseline. I did a paper about this back in like 2004, where I took Hal Puthoff's PV model, which is an analog of curved spacetime,
Yes.
and I looked at it from what would it look like on a flat tangent plane. So what would it look like if you took the PV model and wrote it and revised the mathematics to describe the same thing without a variable speed of light? And
Mhm,
what you get is a variable density function
mhm.
instead of a variable impedance function, instead of a variable refractive index, instead of it changing the speed of light, 1 over mu naught E naught square root, it affects mu naught over E naught, the impedance function. But there is a complete, mapping, one-to-one mapping of all the equations over from one to the other. And that mapping depends on dividing by different multiples of Planck scale objects.
Mhm.
So you would map length from the curved space-time model to the flat space-time model by dividing length squared by the Planck length squared. And then using the density function, the impedance function, would map what that would be in terms of a refractive index in a polarizable vacuum model. And so it really is nothing more than a baseline for mapping one frame of
I
reference to another.
I
And so
disagree, and let me say
it's
why. Let me disagree with you. All right, Todd, we find this Planck force in the general relativity equations of
yeah,
Albert Einstein,
yeah.
which
It's
they
force relative
shouldn't
to the
be
Planck
there.
force.
The Planck force, which is a Planckian quantum, actually, if you think of it, it's the only Planckian variable, or rather, the only Planckian parameter that does not have h bar in it, does not have the quantum of action in it,
It does. It
which
just
means,
canceled out twice.
that it can operate on the classical realm as well as the quantum realm.
It's
Why?
true.
Because it talks to a super density. Remember, a super density, if you think of the Planck force, think of it like the force is on the order of a pressure times an area. So what we're talking about is like uh, the super density times c squared times L squared P, where LP is the Planck force. That super density comes out to be on the order of c to the fifth divided by g squared h bar.
Mhm.
So it's on the order of 10 to the 96 kilograms per meter cube. 10 to the 96 kilogram per meter cube. Well, I'm arguing there's an analogy between our mechanism of supernovas based on core bounds and how the superforce gives rise to a superbang at the super density.
Okay.
This
That
may
makes
be a
sense.
whole different perspective on inflation. It may actually give us, okay, my question is to the illustrious mainstream physicists. I ask, what is a Planckian parameter doing in general relativity? Because you can actually
can I answer that?
No, let me finish and then you can answer any, I promise. But this I must say, because it gives a certain conclusion. It reaches a certain conclusion, in my opinion, a new perspective on all physics. Now, it's not new physics. It's a new perspective on all physics. And this is it. If you look at Einstein's G sub mu nu on the order of 1 divided by Planck force or super force times T sub mu nu, it actually says space-time curvatures on the order of 1 divided by the super force times the whole thing times T sub mu nu. Now, these are same rank tensors. They have to be. Otherwise, right? That's a scalar parameter. Put it on the other side. What does it say? It says the superforce acting as a linear operator on the local spatial-temporal geometric structure gives rise to energy density, hence matter. Do you remember a certain, and this is why I question.
You're saying.
No, listen, just one more thing, and I promise you can talk for the rest of the thing, but this is important because I'm putting it out. Tim might want to cut this out because maybe mainstream physicists listening to this will say, my God, this is total crackpot. But what if 3D printing out of space-time fabric is feasible based on the action of the superforce? If we can nudge the superforce, we can actually, maybe this is how quote unquote ET tech works. And this is what I'm really weirded out by. The way Bob Lazar describes the sports model, saying it's as if it was grown out of space-time itself. Well, this freaking equation talks to that. What if this guy is not full of shit?
Well, doesn't that goes to entanglement and quantum teleportation and things like that?
Oh, that
also,
too,
right?
of course. But it also goes to something he said, which is very strange. Anyway, yeah.
Well, to get to back to your question, and that comes out because I mean, and John would probably verify this too in GEM, that if you look at what is the gravitational impedance equation, you're going to get G over C squared. And in terms of Einstein's equation, when you want to convert from energy density and go to curvature, which is what everything has to be in to do geometry, the unit of conversion from one to the other is 1 over the force. And just like I was saying, the most natural baseline to use, which really has nothing to do with quantum mechanics, it has to do with how we classically defined our units of measure, would be to reference energy density to the Planck force. So energy density over the force gives you square meters, which is curvature. And that's just the natural way things would go. It's classical. It's not quantum. It's classical. But even classically, our human defined units of measure, the way we defined a meter from the king's thumb to his nose, is referenced in all of those constants because it's referenced in energy, and Planck's constant converts from energy to frequency and force, and Newton's constant converts from energy to force, and they're defined on units of measure that we created as human beings. And John likes to work in CGS, and I like to work in SI. His CGS numbers drive me nuts.
I worked in SI.
I have to convert everything when I read his paper. But this is just.
I don't like dragging the factor of pi or 4 pi.
I agree, but it was drummed into me so long, talking with so many other people.
I know.
If I don't do it that way, it just confuses everybody else.
I can testify that that is true.
Yeah. But anyway, so what I want to say, Sal, is that I don't believe in space-time. I think that's a misinterpretation. General relativity does not, Einstein's equation does not say what people think it says. What it says is that given the right-hand side, T mu nu, this is everything we know about matter and energy and quantum mechanics and the strong force and the weak force and all the other forces all fall under T mu nu. And given instruments made of matter, clocks and rulers made of matter, under the conditions set forth by T mu nu for the volume of space-time we're talking about and the matter in it, it describes what we will measure on the left-hand side using rulers and clocks made of stuff from the right-hand side. And space-time is no more or less than what we measure with rulers and clocks and instruments made of matter and energy. It's not a fabric. It's not a thing. These are the things. T mu nu. These are the things. Everything else on the left-hand side is the stage. And we measure what we want. What we measure is due to the quantum interactions between the things, not the stage.
Interesting.
So a ruler contracts in a gravitational field because the probabilities, the probability amplitudes for all that matter interfere with each other and cause damping. And when you add just a tiny amount of damping to a quantum harmonic oscillator, its wavelength contracts and its frequency slows down. So all you have to do is consider in our normal quantum mechanics that if you simply consider the damping that takes place because of non-coherent interference or incoherent interference between matter, and what that does to the atoms, which are just spherical harmonics, they're going to contract, they're going to slow down, and it explains gravity without ever invoking the need for a space-time manifold. The manifold is something that we measure using matter and energy.
I like where you're going. I was gonna add some
This is
humor,
why it's so hard. This is why it's so hard to mate general relativity with quantum mechanics, because general relativity is not needed. It's an interpretation. It's a misinterpretation.
Can I say something?
Please. And Jeremiah.
Okay, let me say this, and then Jeremiah can take the next thing. Okay, I believe, it is my strong belief that Einstein's general relativity is not only correct, but is actually extremely close to the final solution. I think he was extremely close to it. The reason that anyway, I'm not going to go into the reason why he could not come up with a unified field theory. Only a great like Einstein would go there. So I am just a mere apprentice of the man. What I'm trying to say is that the superforce equation would not hold correct if there was not a link between the realm of the very small and the realm of the very large, the observable universe. The superforce equaling the energy gradient at both the Planck scale and the observable universe scale known as the horizon scale, that cannot be a coincidence.
No, it's not.
And that comes right out of GR. So if GR is wrong, everything else is wrong, including what? The freaking Dirac equation, Schrodinger's equation that has been proved over. And why? Because we find, I look toward the first segment of this where I explain to Dr. Brandenburg exactly how I find the superforce in the Schrodinger equation. How can the Schrodinger equation show the superforce is there if the superforce was not important? And the superforce also is important. You cannot tell me that Einstein knew that was the Planck force. I do not. Einstein refused to believe in quantum mechanics. As a matter of fact, he was very much against it. The Bohr-Einstein debates are some of the most fascinating dialogues in the history of science. It's absolute amazement. I mean, the idea of quantum entanglement, wow. And I tell you, Bohr almost lost the one based on Einstein-Rosen bridge, the idea of ER equally. Anyway, Bohr almost lost that one. And then he remembered that Einstein wrote this little something. He actually used Einstein's own writings against him. That's how Einstein lost the final debate. Can you imagine having your own work used against you? Todd, I would have freaking died. I would have been so pissed. I would have knocked Bohr through the wall. I don't care, you know what the.
I was on Usenet in the 1990s. I got a skin as thick as a turtle.
Very good.
That's right.
That's good. It's good to have that skin.
No, but between you and I, hey, Doc, would you agree with me? When people get physical, you know they love the physics.
Yep.
Yeah, that's true.
That's for sure. Hey, well, so that relationship you mentioned, did you know that if you take the Walker-Robinson equation and the reciprocal interpretation of that equation, and you take the Hubble constant equates to, say I had a meter stick in my hand. Okay, the Hubble constant equates to this meter stick contracting 6.8 nanometers every century.
Oh, wow.
So if the size of this meter stick depended on the quantum environment here, causing it to have this proper length, and here energy is running down and decreasing such that my meter stick is contracting 6.8 nanometers every century. And I look back in time as I look out into space, and if everything were doing this from a common Big Bang or a common starting point, then what I would see is everything will appear to be accelerating away from me and redshifting because my ruler is getting shorter relative to those wavelengths. And so that would connect the cosmic horizon to the smallest scale here on Earth.
Jeremiah needs to speak.
Yes, please.
Jeremiah, go ahead, sir.
Okay, so in one model here, Todd, you're presenting us with a stress energy momentum density equivalent in space-time that allows us to calculate out the, well, curvature equivalence, or in the more correct terms, the actual energy momentum in any given volume of space and its gradient, if one should apply, particularly in mass. The issue with it is, well, the mechanism of action there for curvature does not actually reveal the underlying substrate that causes the curvature to take place in the first place. So
yeah, it does. I said it was. Go ahead.
Well, it's field force interaction based on measurements, but they don't actually reveal the underlying substrate of why there is said distance over X space and time. Hence, if it's beyond the probability scale, we have to acknowledge the particle pair and the tremendous number of particle pairs in each unit of Planck distance. Because without that, we don't actually have an explanation for why the mass energy density or the angular momentum or the other various factors of that localized space has the properties that it does have. So we have to acknowledge that it has some properties that are very much like mass.
You're making an assumption that it has a property without interacting with anything else.
Well, we have various factors that are within already our very well recognized mathematics, like the local K of our space-time, the refractive index. We have our epsilon and mu. We have our G.
You hit on it.
You're misinterpreting what I'm saying based on your understanding.
Cosmological constant, the gravitational constant, these things have to be defined by something. There's got to be something there to define them. And that's what I'm saying.
Yes,
It's like,
there
You
is.
got it,
There
Jeremiah. You got
is,
it.
and it should
You
all
got
be included in Team You Knew.
Mm-mm.
Everything, all stuff is in Team You Knew. The vacuum energy is in Team You Knew. It's
What?
part of it.
No, no, that's a cosmological constant that he brings
It's
in.
it can be
on the
added
other
in there.
side
Team
with-
You Knew can have a
with the
constant.
Riemannian curvature and the Ritchie tensor. He also adds
Team You Knew can have a constant
he also
added
adds
to
the
it.
lambda.
Team You Knew
It's
can
on
have
the
a
left-hand
constant added
side.
to it. It doesn't. It
That's
doesn't have to
so-called
be a
dark
separate
energy.
entity.
Vacuum energy.
I'm saying that if you take away Team You Knew, there is nothing. There's no particles popping in and out of
I disagree.
existence. There is
I
just a stage.
No, no. The quantum vacuum
It
is
has
a material
no
medium.
matter.
to be.
If there is no
Otherwise,
matter,
neutron
there is no
zero and
thing.
epsilon
If
zero
there is
would
no
not exist.
thing, there's nothing.
No. I totally disagree with that. The
You
quantum
have to have a
vacuum
field.
has a
Sal, you have to have a
Look at-
field. The particles come from the field. The first entity you put in the vacuum
Look at
is a
Frank
field.
Wilczek's work. Look at Frank Wilczek's work and the idea of materiality of a vacuum.
I don't like Frank Wilczek's work, to be honest.
Well,
I've read it.
I
I
do.
don't agree with them. I'm more likely to agree with I can never remember his name. I'll think of it. Never mind.
I think
But-
the man is a genius and deserves another Nobel Prize. How's that? And I mean that.
It
Well-
makes no sense to me, to be honest.
It makes total sense to me. As a matter of fact, the idea that they would take his axion and pervert it, and I'm totally against it. I think they should find the original axion, his axion, not this one Kathy Fries is looking after. She was on Brian Keating talking about it. Anyway, yeah.
My point is that I look at it is that you have to start with a field. You don't start, the empty vacuum has no shape. It has no particles. You have to add a field before you have any pair creation. Before you have any particles, you have to add a field. And as soon as you add a field, it's not empty anymore. It's not space. It's not empty space. It's space filled with a field. You can't measure time until you have a particle that's moving to clock it.
What do you think time is, Todd? What do you think
Time is what you measure with a clock.
No,
Give me a
no, no.
clock, I'll measure
Physical
time.
time. What's physical time? Do you
What
think,
you
for
measure with a
example,
clock.
physical time can have multiple dimensions, like space could have
No,
multiple?
nonsense.
No?
It's nonsense. Physical time is what you measure with a clock. That's all it is.
Eric
no
Weinstein
fourth dimension.
illustrated it greatly.
There's no fourth dimension. Now is all that
No,
exists.
Todd, time is the expansion of the universe, basically.
Yeah,
That's really the best clock for time that we have.
yeah. I don't believe
it's
in
an
the clock
accelerated
universe. The past
expansion.
still exists and the
It's an
future already
accelerated
exists
expansion,
and
so
everything
it's
is predetermined.
Quality
I
of
don't buy
time
that.
is an energetic informational field.
Yeah,
Since we're dealing with an accelerated
That's a
expansion
clock.
of the universe. Yes, but it's a collective field. So what is it made out of? The things
particles.
that are. I'm saying our understanding of physical time is inadequate. We should research
Our
it further.
understanding of physical time in general is very confused.
Mm.
Even among physicists in the mainstream. What one physicist says is time and another physicist calls time
Agreed. Like
completely different.
Carlo Rovelli thinks very different than Julian Barbour thinks very different than Lee Smolin. I do agree with
I
that.
take it down to the
All
basics.
makes sense.
Time is what I can measure with a clock.
Mm.
That's my observation.
Yeah,
can
but that's
any
your
clock I
engineer's
want.
look to it. You have to step back and look at the fundamental of it. What is physical time?
I don't believe there is a physical time because I can't measure it.
You can measure
I
heartbeats.
think it has a lot to do with
That's a
entropy, the
good
state of
clock.
entropy, phase transition.
I have a great ticker right here.
You know, so you're saying basically, until you measure it, there is no time.
Exactly.
Oh,
Okay, I
Time is
understand
what you
that.
can
I understand.
measure.
I grasp that.
so
Well,
to you,
and
time is
just
an
to-
illusion.
If you
If I
can't
could
measure it, it don't
To me, it's
exist. It has no
physical.
effect.
It's a physical entity. Lee Smolin agrees with that. Time is real. Julian Barbour and Carlo Rovelli believe in time is more of an illusion, an illusory entity. I believe Lee Smolin is correct. Time is very real. Physical time can not only be altered, it can be manipulated. But that's me. Eric Weinstein also believed in multiple dimensions of time, just like we have multiple spatial dimensions brought forth by string theory. One should not put down string theory because you disagree with the lack of experimental verification, period.
I like
Okay,
string
because it looks to me like
It
Maldacena
leads to
came from
conformal
an
gravity, and that's what
experiment that was
I have as
performed in
conformal gravity.
1968.
So
Anyway, yeah, I mean, we agree to disagree. This is the
so
beauty of physics.
if I let me, so John mentioned time being related to the expansion of the universe. One thing I have wondered, I'm going to showcase how dumb I am right now, but
Nah, you're not dumb.
if the
You're
universe
not
is
dumb.
what the
Damn,
universe
you're organizing this conference.
Then
Well,
I'm a certified idiot.
the universe is one. The universe is like unity, right? The universe is one. Is the universe expanding, or is maybe the universe staying the same size and everything in it is becoming more detailed? Maybe losing energy and shrinking. Not shrinking. Shrinking is a bad word, but dissipating.
I believe
Becoming more
every
entropic.
unit is contracting.
I know I'm splitting hairs, but it's one of those paradigm changing. This occurred to me a while ago.
Oh no, and paradigms, concepts are extremely important. That's why the
John,
super force
Mathematics says it could be either way, Tim, because if you look at the equation one way, the universe is expanding and everything else is staying the same size. If you look at the equation the other way, the universe is the same size, but we're observing it from a contracting galaxy, from a contracting.
Yeah, well, so maybe that contraction is the actual function of entropy.
Can't tell the difference. There's no measurement you can make to tell the difference.
I know. That's
Have you seen Roger Penrose's idea? Instead of inflation, what could birth the universe? Have you seen his cosmological theory?
Yeah, but I don't understand the connection between an absolutely everything's evaporated and there's nothing left, and then suddenly you've got a singularity to start a new one. I don't buy that. In Roger Penrose's cyclic universe,
Have you read
he ends up with nothing, and then there's a new singularity. Why?
Have you read Abai Ashtekar? He talked, okay, in this book, if you ever have a chance, get Conversations on Quantum Gravity by it's a compilation of conversations with greats like Nima, Juan Maldacena, Abai Ashtekar, right? By Jacques Armas. Read carefully the part, not only Juan Maldacena, but read Nima as well, but read Abai Ashtekar especially. The part on the quantum bounds. It is freaking pure genius. I think this is how it was done. And it talks directly to the superforce. You see, the quantum bounds has an analogy to supernovas. And let me explain. Can I explain why I'm saying this? Okay, and tell me if the physical mechanism makes sense to you. Please do, because this is important to me. As you well know, in a supernova, once the fuel runs out, it starts imploding. It comes to, say, on the order of 10 to the minus 15 meters. So we're talking about 1 femtometer. That's the realm of the strong nuclear force. It resides at 10 to the minus 15 meters. So we're talking about the strong nuclear force is there. Now, the densities we're talking about is on the order of 10 to the 14 grams per centimeter cube. So again, not exactly small, but not exactly Planckian either. So because of the strong nuclear force, there is a core bounce. It basically tells it tells the implosion, stop. You shall not go any further. This thing rebounds and it explodes. Hence the supernova. Well, I'm saying there's an analogous mechanism with a superforce at the super density on the order of 10 to the 96 kilogram per meter cube. This contraction, it undergoes what Ashtekar calls quantum bounds. I call it an Ashtekar bounds. The whole idea is that the superforce at 10 to the minus 35 meters at the Planck scale tells the mechanism, you shall not go further. And again, this thing undergoes a quantum bounce, hence the formation of a new era, a new epoch of the possibly a new universe. But why not a super intelligence? Do you realize that most of our universe, you know, the work of Anthony Peratt, 99.999% of our universe is made out of plasma. Remember the Bussard ramjet, the whole idea of, you know, yes, you need huge scoops and all that, because again, the energy density is extremely low. It's on the order of 10 to the minus 9. It's not, you know, we talk about 120 order of magnitude difference between quantum field theory and general relativity as far as the vacuum energy density is concerned. Yes, it's true. But if it is plasma, check this out. Just hear me out. This sounds a little bit weird. But what if plasma under certain conditions has a capability of sentience, consciousness being activated on a macro scale? So basically the universe becoming a super intelligence, not an artificial super intelligence, but a natural super
That's
intelligence.
beyond my pay grade, man.
I'm just saying the possibility may exist. That's all. I'm just putting it out there.
Yeah.
So what I'm saying, I'm talking about something I call the triarchy of creation. Super force based on the super density, which again is Planckian, because the super force bridges the realms. So super force leading to super bang, leading to super intelligence. I call it the triarchy of creation. It's just an idea. It's out there.
No, I was listening to
worse
Brian
things have been
Green and
brought out.
Sabina Hassenfelder telling me that the universe is deterministic, and I'm like, that doesn't even.
Well, in a way, if the super intelligence exists and it controls everything, yes, it is. It is deterministic. If such a super intelligence would, basically, this super intelligence would have the ability.
I binge watched Loki last night. You should watch it because that's what the end was.
I mean,
No, that's
Loki is very intelligent.
Huh?
If we're talking about time, people should watch.
Loki.
He finally got what he wanted.
The Norse god, was he brother to Thor and all that? Odin.
Oh, yes.
no, he was the child of Odin with some
Because he was
giantess or something.
Right? Yeah.
It goes off on a tangent and it goes into this. Basically, he does something that he's not supposed to do, and the time police arrest him for creating a new timeline, and they're about to erase him, and then they use him to find another Loki who was off on another tangent, and it just becomes this whole time traveling bonanza.
Let me bring it back. Mark, let me bring it back to super intelligence, because I think this is important. Let me bring about another analogy I've always wondered about, and let me throw it out there. The human brain supposedly contains on the order of 100 billion neurons, synapses and such. Our so-called observable universe has 100 billion galaxies, each with 100 billion stars in it. So again, this number, if you believe in the Dirac large number hypothesis, it's possible to make the analogy, what if this super intelligence is really a Boltzmann brain? You're acquainted with a Boltzmann brain. You know, Sean Carroll talks about it all the time, you know, as a popping. What I'm saying is, what if this super intelligence exists? What if this is what we're talking about? What if it reinvents itself with a quantum bound just to auto-experiment on new possibilities? I know this is wild speculation, but I'm saying what if, and it's all based on the state of plasma. What if plasma, under certain conditions, can become sentient?
Well, there are several authors.
As a working plasma physicist, I can tell you the plasma is sentient already.
Really? How would you
It has a mind of its own, and you have to convince it to do what you want, but you can't try and force it.
Interesting. Very interesting.
There have been several authors that have hypothesized that. So, and I don't remember the name of it. Pete Gerritsen told me a book that he was really excited about.
Oh,
that apparently-
Gerritsen, interesting guy.
Yeah, and he just finished a big book, and the idea in that book was, what if plasma filaments in
Is
galaxies?
it bigger than this? Is it bigger than this? Is it bigger than Roger Penrose's epic, in my opinion? The road to reality, 1,050 pages of absolute genius. This man should be lauded by King Charles III of England.
None of the road to reality is long.
If you ever
It's
listen
long.
to
It's
this
a long
podcast,
road.
if you ever listen to this podcast, please, Lord, yeah, absolutely, peerage all the way. This is a beautiful book. This is this is a must-have, along with a Superfluid Universe by Kirsten Wong and Carver Mead's Collective Electrodynamics. Unbelievable. Those 3 books, baby. I don't know what I have with the number 3. It is what it is. Anyway. Yeah. Okay, I'm done.
Yeah, well, no, thank you. I mean, yeah, in terms of recording, so I would love to be able to put this up at APEC. You know, I'll edit. I will edit heavily. I will edit. We'll probably end up with about an hour of usable footage, but that's okay.
Please make sure that whatever we say about mainstream physics is laudatory. We want them to engage with us, bro.
Oh, yes.
We don't
Skip
want them. We
my
don't want
comment
them
to
stay
Brian
away.
Green.
Definitely. No, we want them to start being more malleable, more, like take us seriously. Right
why
now,
don't
they're
I?
thinking we're all crackpots.
So why don't I
That's the-
stop? Let me stop recording now. I'm going to stop
Okay, yes,
recording,
start recording,
and,
yes,
and
stop
let me
recording.
let me thank you guys both. And
Yeah, I want to thank
we'll
you.
stop
too. That was
recording
great.
now.
Thank you
all.
all. Thank you. Thank you
Been
for having us.
wonderful.
Tim. Wonderful as usual. You have the absolute best interviews, bro. Listen, anybody that likes John Brandenburg and Salvatore Pais, please
No,
subscribe.
Sal, come on. Yo, Sal, you're the guy who invented the super force.
Nah, man, you invented gym theory. I mean, you gave life to the pointing vector. Everybody had forgotten about how important the pointing vector was. Anyway.
That's how I know there's a God, by the way, because he's a punster.
Okay.
The pointing vector points in the direction of the momentum flow, even though they're spelled different.
On that
Right
note,
on.
let me
For
thank
Warp
you.
Drive
Let me
Tech.
thank you both guys, and Todd as well, and everyone, Jeremy Riss and Jeremiah Pop and Mark Sokol. Thank
All
you guys.
right. Live long
Thank
and
you.
prosper.